Thank you so much. Thank you for the invitation and thank you for the introduction and the shout out to Jawscan, about which I will talk towards the end of the presentation. So yeah, as Ben said, I am Dani Arias-Rotondo. My students know me as Dr. Dar because I always joke that my last name is too long to say. And I will use this first slide to give you a very brief overview of my life and career, and then I will jump onto the science. So I was born and raised in Buenos Aires, Argentina, and I was mostly educated there. So I did my undergrad at University of Buenos Aires. And when I was there, I discovered both ruthenium chemistry and photophysics, and I thought that that was the coolest thing ever. I kind of still do. So after I graduated from undergrad, I moved to Michigan to go to Michigan State, and I did my PhD with Jim McCusker there, looking at ruthenium photophysics. And that allowed me to do a collaboration, which is the story that I'm going to tell you about today. And I then went on to do a postdoc with Dave McMillan at Princeton doing Photoredox Catalysis. So you start seeing the theme here. And since last year, I am at Kalamazoo College, which is in Michigan. So if you know what Michigan looks like, it's right there. Oh, you cannot, I'm doing the hand thing, but you cannot see it. It's in the southwest of Michigan. It's cuter when I do the hand signs. Anyways, and so I started at K last year. Today, we wrapped up our summer of research, which was pretty amazing. So if towards the end you have questions about what it is like to be an international graduate student, or what it is like to be at a small liberal arts college and doing organic research, I'm also happy to talk about that. Anywho, let's get to the science. And so I am an inorganic chemist, but today I'm going to talk a lot about organic chemistry. And you may or may not be aware of this, but we have a lot to thank organic chemistry for. Okay, synthetic organic chemists have really changed our lives, not just because of all the different reactions that they have developed and all the technology that they have developed, but also because of all the things that we can make thanks to organic synthesis that make our lives better. So if you look around the room that you are sitting, laying, standing on right now, you'll see a lot of things that we have thanks to organic chemistry. And so here you have some examples. Some of them are quite important to me, like, you know, the Argentinian soccer jersey or Legos, but in general, lots of things that are, as I said, very relevant to our lives. And in particular, what I'm going to talk about is Photoredox catalysis. And the reason why I highlight those maths there is because Photoredox catalysis, even though it could be quite interesting for many things, and that is a point that I will get back to at the end of this talk, Photoredox catalysis has received most attention from pharmaceutical companies. And a lot of the research efforts and the collaborations that happen between industry and academia are in Photoredox catalysis, or I should say, there are lots of collaborations between academia and industry that focus on Photoredox catalysis. There are lots of pharma companies doing Photoredox catalysis. So that's kind of the connection there. So Photoredox catalysis as a field, so Ben in the intro mentioned photochemistry, and photochemistry is not a new thing. It's been around for decades, but Photoredox catalysis as a subfield within organic chemistry is commonly accepted to have been born in 2008 with two papers that I will show you here. I'm not going to discuss the papers. I'm going to very briefly give you an idea of what they were about. So the first one came from the Macmillan group, where they took these aldehydes and these racemic alpha bromocarbonyl compounds, and they combined them in the presence of a ruthenium catalyst, an organic catalyst, and some blue light at room temperature, and they got these enantioenriched alpha alkylated aldehydes. And the important thing for this talk is that this is the ruthenium complex, the photocatalyst that they use, this ruthenium tris bipyridine compound that I will refer to as RuBP or RuTris-BP. And they also had this organic catalyst. The other important paper for Redox catalysis is from Teshik Yoon's group, where they took these enones and also using a ruthenium photocatalyst in the presence of blue light and at room temperature, they got these 2+2 cyclo additions. And again, the photocatalyst that they used for these reactions was also RuBP. So here are the mechanisms that they proposed for these reactions, and I'm not going to go over them in detail because we will look at other mechanisms in a moment. But what I do want to highlight from both of them is that they both include this cycle where RuBP absorbs a photon, gets to an excited state, and then it does some electron transfers to get these reactions going and to keep them going. So that is the first thing that I want to talk about and kind of get out of the way here, is that for photoredox catalysis, the photoredox catalysts tend to be transition metal compounds. There is, full disclosure, there is a branch of photoredox catalysis that uses metal-free, so fully organic photocatalysts. I'm not going to talk about those, but I would argue that to this day, most of the photocatalysts that are used are transition metal-based. Because the original reports used RuBP, and because I worked with ruthenium photophysics for my PhD, I'm going to give you this intro using RuBP, but then I'm going to shift to iridium later, and the mechanisms, the basic ideas are the same. So the reason why we use these photoredox catalysts is because they can absorb visible light. They are intensely colored, they absorb visible light, and they use that energy from those photons to promote an electron from the metal center to the ligand. So we started here with a ruthenium-2 center and some neutral ligands, and now here we have a ruthenium-3 in our excited state and a ligand that is reduced, that has an extra electron. This type of excited state we call a metal to ligand charge transfer excited state, or MLCT. And one of the first things that I should highlight is that because these photocatalysts are colorful and they absorb visible light, we can selectively excite them in our reaction mixture. So if you are familiar with organic compounds, they tend to be colorless, which means that they absorb higher energy light, UV light. And for this reason, if we have a bunch of organic molecules in our reaction mixture and we have some RuBP, for example, and we shine blue light, the only thing that is going to actually absorb that blue light is a ruthenium compound. So even though there are other things in the solution, the only thing that we're going to excite is the photocatalyst, and we're going to leave all the other substrates alone, which is actually a very elegant way of delivering energy to our reaction, as opposed to just heating up our whole Rambourg flask and hoping that things work out. Now, when we have this charge-separated excited state, if we look at this reduced ligand can give up that electron, that extra electron that it has, to something else in the solution that would be acting as a strong reductant. And in that case, we would get this ruthenium-3 species that you can see here. On the other hand, that ruthenium-3 species, or that ruthenium-3 center in our excited state, can act as an oxidant. It can take an electron from something else in the solution. And in that case, we would end up with these reduced ruthenium-2 reduced ligand species. And so if we have these after gaining an electron, taking an electron from something in the solution, we still have that reduced ligand that then can give up an electron to something else in the solution, go back to the ground state. And so another advantage of these photoredox catalysts is that we have both an oxidant and a reductant in the same reaction vessel. So instead of needing to put some chemical species that reduces other molecules and some chemical species that oxidizes other molecules, we only need one species and some photons to get both reductions and oxidations happening in a reaction mixture. So photoredox catalysis, as I said, has been around since 2008 as a subfield of it on its own, and it has shown a lot of promise. It has opened the doors to some transformations that were not possible before. But more recently, organic chemists have gone like an extra step and started what some groups call Metallophoto catalysis. And so in this case, Metallophoto catalysis, apart from being a mouthful, is the combination of two catalytic platforms to really get an enhanced reactivity. On one hand, we have Photoredox catalysts. So now I'm showing you an iridium photocatalyst just because those are the most common ones in this area. But again, they work very much like the ruthenium compound that I just showed you. And so in general, these compounds absorb light and then they shuttle electrons around. They do oxidations and reductions to other things in the solution. And this is combined with more traditional transition metal catalysis to do what we normally call cross-coupling reactions. So by combining this Photoredox catalysis and these transition metal catalysts, we can now have a new catalytic platform that can go beyond what either of these two could do on their own. So like the old adage of the total is more than the sum of the parts, it is true, right? So really there is, I don't really like the word, but there is some synergy here between these two catalytic platforms. Now, to give you an idea of what Metallophoto catalysis looks like before I start showing you the work that I wanted to talk about today, I'm going to show you the very first report on Metallophoto catalysis, which was a collaboration between Avi Doyle's group and Dave McMillan's group, and it came out in 2014. So here we have an alpha amino acid and an aryl halide, and these, in the presence of an iridium compound, a nickel compound, and blue light, give you this benzylic amine. And here you have the two catalysts that were used for this reaction. So we have this iridium photocatalyst. It's a bit fancier, some more substituents than the rubipi that I showed you originally. But again, same idea, absorbs a photon, gets into this MLCT excited state, and then it can give or take electrons. And then we have this nickel catalyst that can do your traditional cross-coupling steps, so like a reductive elimination and oxidative addition, that kind of thing. And I do want to take a look at the mechanism for this reaction and walk you through it. So we start with our iridium-3 photocatalyst. As I said, it will absorb a photon, get into an MLCT excited state. And then this MLCT excited state can take an electron from the alpha amino acid, give you this alpha amino radical that you can see here, and an iridium, a reduced iridium species. On the other hand, we have our nickel compound, which starts as a nickel 0 species. And this can do an oxidative addition into a carbon halide bond to give us this nickel 2 species right here that can then react with the alpha amino radical that was formed thanks to the iridium photocatalyst. And we get this nickel 3 species right here. And it's important to see that both parts that we are trying to couple together, these two fragments, are now attached to the same metal center. So a reductive elimination gives us the product and this nickel 1 species. And finally, if this nickel 1 compound reacts with our reduced iridium species, now they can close both cycles by doing an electron transfer and getting back iridium 3 and nickel 0. A couple of things to keep in mind from here. One is that in this case, our starting materials are actually fairly cheap and bench stable. So in this case, they are using aryl halides and alpha amino acids. And alpha amino acids, in this case, this particular one, is pretty much dirt cheap. So instead of needing the very high energy starting materials that a lot of traditional cross-coupling reactions need, we can use things like amino acids. And the other interesting thing, not so much from the point of view of organic chemistry, but again, going back to I am an inorganic chemist. One of the cool things about this reaction mechanism is that there's evidence of these different oxidation states that are a bit unusual for nickel. So usually the chemistry of nickel for the most part is nickel 0 and nickel 2. And here we have nickel 3 and nickel 1 species as well. So now to move to some of my work in this area, my story focuses on this reaction right here and these two guys who were grad students in Dave McMillan's group when I was a grad student in Jim McCasker's group. So Eric and Chip were working on this esterification where they started with a carboxylic acid and an aryl halide, and in the presence of an iridium compound, a nickel compound, and some blue light, they got this aryl ester product. And so if you don't know how Photoredox catalysis and then like methodology groups work, usually when you have a reaction that you have an idea that it's going to work or it's kind of working, you do an optimization, which means that you try as many, in this case, iridium catalysts and nickel complexes as you can find and see which one gives you the highest yield. Now, during this optimization work, one of the things that they noticed, one of the first complexes that they used, is this iridium complex with these fluorinated phenylpyridines. And the reason why they tried this one is because this compound is pretty much the workhorse of Photoredox catalysis. And part of that is because in its excited state, it's a pretty good oxidizing agent. So it tends to be really good at generating, for example, nickel 3, similar to what I just showed you in the previous slide. But the interesting thing about this was that these photocatalysts that usually works for pretty much everything did not work at all for this reaction. And interestingly, when they used the simpler iridium PPY3, which is much less oxidizing in its excited state, they got an 85% yield. So this was odd because if forming nickel 3 so that reductive elimination could take place was such an important step, in a step like definitely necessary for this reaction to go to completion, why was the photocatalyst that didn't do that oxidation as well, why did it work so well? And so another thing that they tried was wow, the moment when you forget the name of the molecule, can you believe this? Benzophenone, there we go, thank you. When they tried benzophenone, which is not a redox catalyst, but it's usually an energy transfer catalyst, they got a 25% yield. So at this point, they were quite confused, and this is when Dave McMillan picked up the phone, called Jim McCasker, and we put all of our, we joined efforts to understand how this reaction was working. Because the question that we had here was, could it be that this activation of the nickel catalyst is actually happening through energy transfer instead of electron transfer? So if we go back to our excited state photocatalyst, so we started with iridium 3, so in the excited state we have iridium 4 and this phenylpyridine that is now negative, it's reduced. What I showed you before was that either these could get reduced or oxidized by exchanging electrons with other substrates in the reaction mixture. But what if instead of doing that, what if it's actually transferring all this extra energy that it got from light onto the transition metal catalyst? In that case, we would get, the iridium would go back to the ground state, and we will now have an excited state transition metal catalyst, and who knows what that can do. So that was our idea when we started collaborating on this project. We were trying to figure out if this was the case instead of the electron transfer activation. So here is the mechanism that we thought we were working with. The idea was that we started with a nickel 0 species. these species would do an oxidative addition, just like I showed you before, onto this carbon bromide bond, and we would get this nickel 2 species here that then would react with a benzoate anion that was part of the solution and give us this nickel 2 species. And again, you can see here that just like I showed you before, now we have both fragments that we're trying to couple together. They are both attached to the same metal. And now, since they are both attached to the same metal, a reductive elimination should get us to the product. Now, the problem was, we knew from previous work that a reductive elimination to form a CO bond is actually very sluggish from nickel 2. So our question was, how is a photocatalyst facilitating this step? What is happening here? And we had basically two options. One was, again, going back to what I showed you before, it would be the analogous step. So we would have this nickel 2 species, our excited state iridium photocatalyst, and there would be an electron transfer where the iridium photocatalyst would act as an oxidant. It would take an electron from nickel, give us this nickel 3 species, but then it could undergo reductive elimination, give us a nickel 1 species and the product. But what we thought was happening, because remember that the photocatalyst that was really good at generating nickel 3 wasn't doing this very well, what we thought was that instead this excited state iridium was transferring all that extra energy onto the nickel species, getting us this nickel 2 excited state complex, and then that was undergoing reductive elimination. So our goal here was to really figure out, to see if we could prove that this was the case or disprove it and understand how this reaction was working. So here the dotted line is this confusing step, if you will. And what we thought was that we had this excited state nickel 2 species that was acting as a key intermediate for this reaction. And we thought that we were accessing that excited state via energy transfer from the excited state iridium complex. Now, one of the things that Jim and I as photophysicists thought was that there was nothing special about that excited state of nickel 2 that meant that it couldn't be directly accessed by shining light on the nickel species. So we thought that this excited state was probably something that we could access by just shining blue light onto the solution with only the nickel complex there. So one of the things that we did was actually try this reaction in the absence of any iridium photocatalyst. So we put the carboxylic acid, the aryl halide, the base, the solvent, all the different things that we needed, the nickel catalyst, and we shone light on it. And the reaction took much longer, and the yield was fairly low compared to the 85% yield at 18 hours that we got with iridium, but the reaction still worked, which told us that indeed we were able to access this excited state through direct excitation of nickel without using iridium there. It wasn't as efficient, but still. And so the step that we were really interested in probing was this, right? I keep going back to it. And if you're trying to probe this step, what you would like to do is to synthesize this key intermediate complex where you have, as I said before, both fragments that you're trying to couple. They are both already attached to the same metal center. But the problem is that, unsurprisingly, since this is a key intermediate in the reaction, it's actually quite unstable in solution and it reductively eliminates very easily. So instead, we used this complex as our model complex. And so you can see that they are very similar, right? We have nickel 2 in both cases. We have the same bipyridine ligand in either one. And then we have a carboxylate ligand in our original compound is a benzoate. In this case, it's an acetate. But still, you can still see that this part is very similar. And then we have an aryl ligand. But for a bit of extra stability, we use the CF3 groups instead of having the substitution in the para position as we had originally. And so this complex is much more robust, much more thermally stable in solution. And so we were able to synthesize it and do some chemistry with it. And the first thing that we did was actually test its ability to reductively eliminate. So what we did was take this nickel complex, put it in solution, shine light, and see if we could get the reductive elimination product. Now, if we had our iridium photocatalyst there, we could see the product pretty quickly. In about 30 minutes, we could start seeing the product at NMR. Whereas if we shone light directly on the nickel complex without any photocatalyst, it took 60 hours for us to detect the product in NMR. So first of all, keep in mind that this is a model complex, but it's not the actual key intermediate that we proposed. It's a more stable, more robust compound, so it makes sense that it takes longer. But also, if we look at the UV of the UV spectra of these two compounds, both iridium and nickel, you can see that this nickel complex actually absorbs light less efficiently than the iridium complex. So again, this was a pretty solid piece of evidence showing that, again, yes, we can shine light directly on a reaction mixture, and even if there's no iridium there, we can still get a yield. But we wanted to probe this energy transfer step even further. And this is one of my favorite parts of this paper, because we took the reaction, but what we did was run a bunch of different iridium photocatalysts. And what we did was use these bipyridine ligand here. We used different substituents so that we could tweak the electronic and photophysical properties of these ligands just by changing that the properties of this complex just by changing the ligand. So, excuse me. So what we did here, as I said, is look at this series of photocatalysts, and you can see on the table that they have different excited state energies. This is the energy of their MLCT excited state. And these are the redox potentials, the oxidation potentials, both in the excited state and in the ground state. And what you can see here is that the reaction yield increases when the energy of the excited state increases. And particularly, there's a very clear cut here between having just plain bipyridine, like the one shown here in the picture, and dichlorobipyridine. Furthermore, you can also see that the oxidizing power of the photocatalyst, be it in the excited state or in the ground state, doesn't track with the yield of the reaction. And in some cases, the higher the oxidizing power or the stronger the oxidant these complexes are, the lower the yield of the reaction. So again, if we're thinking about an excited state, if we're thinking about a mechanism that involves nickel-3, this inability to make nickel-3 would be a problem. So, and all these trends really track with this idea of energy transfer. So if you think about, in this cartoon, we have a y-axis of energy. And so if this green arrow here shows us the excited state energy of a iridium catalyst, we can see here that if the energy of that excited state for iridium is high enough, it's going to be easy and it's going to be favorable for this energy transfer to nickel to happen. Whereas if the energy of the excited state is too low, now the energy transfer is going to be uphill and it's not going to happen. We did some other studies to probe this mechanism a bit more, but I'm not going to tell you about all of them. I'm just going to summarize our conclusions here. So we saw that energy transfer from iridium to nickel is favorable, and that the reaction yield tracks the excited state energy of a photocatalyst. We also saw that our most efficient photocatalyst, this iridium PBY3, cannot oxidize our model nickel complex from nickel 2 to nickel 3, again suggesting that our best photocatalyst is not forming nickel 3, so there's no nickel 3 to do that reductive elimination. And in general, oxidizing photocatalysts, as I just showed you, perform poorly. And what's more, this was yet another thing that we tried. We tried reducing from nickel 2 to nickel 1. And while for our best photocatalyst, iridium PPY3, this reduction was favorable, and we tried doing this reduction with other external reductants, it got us nowhere, which makes sense if you think about the fact that our key step is a reductive elimination. You don't want to reduce before a reductive elimination. But we tried that anyways. We covered our bases. It didn't get us anywhere. So really, with all of this, we were convinced that indeed iridium to nickel energy transfer was the key step to induce a reductive elimination in our reaction. And we wanted to highlight that this was, up to that point, an unthought of activation mechanism for these photoredox catalyzed reactions. So not that we discovered energy transfer. Energy transfer has been known for many, many years, but it had not been invoked as an activation mechanism for these kinds of reactions before. And so going back to this slide that I showed you at the beginning, we showed that not only these photoredox catalysts can do oxidations and reductions, but they can also do energy transfers. And so part of the interesting thing here is, now that we know that we have this new activation mechanism, what can we do with it, right? So what other new transformations can we accomplish by using this other activation mode? But to me, this is not to me the most exciting part or the most exciting take-home message from this paper. To me, the really cool thing was that we had an organic chemistry group and an inorganic / photophysics group, and we collaborated. We really learned to communicate with each other, because sometimes talking across disciplines can be really weird. But we were able to work together to really understand some aspects of this reaction and some of the mechanisms of this reaction. And that was really, really cool. And that is what I want to focus on now. And if you're going to forget everything that I say, remember this, because I really believe in the power of an interdisciplinary approach, the power of collaborating across disciplines, and particularly in the case of photoredox catalysis. So here I want to highlight a couple of papers that have come since our collaboration from different groups. This is by no means an exhaustive list. These are papers that I am familiar with because I know the authors. In some cases, I heard these stories before they were published. So do not think that these are the only ones that are out there. But in particular, I want to highlight this one right here, which is a collaboration between the groups of Greg Skoll, Phil Castellano, and Avi Doyle. So you have an ultra-fast spectroscopist, you have an inorganic photophysicist, and you have an organometallic / organic chemist. And what they looked at was this series of nickel 2 complexes, and you can see that they are very similar to the ones that we worked with. But instead of looking at them in the context of a particular reaction, they actually decided to really study the photophysics of these complexes on their own, so that they could then understand how they work in different reactions. So they prepared these two series of nickel 2 complexes, and they used different substituents both on the bipyridine ligand and on the aryl, and they used electron donating and electron withdrawing groups to really tweak the photophysics. And they did a lot of spectroscopy. So here you have the UV-vis spectra of both series of compounds. They also did time resolve absorption. One of the conclusions that they got was that when these nickel complexes first absorb light, they actually access an MLCT state very similar to the one that I showed you for ruthenium and for iridium. So a state that has a nickel 3 and a reduced bipyridine. But also they did other different techniques from time result IR, they did calculations, they did some NMR studies, and they saw that after this initial MLCT state is formed, it actually relaxes onto a DD state or a ligand field state. And then this state is actually tetrahedral. And they were also able to see that you can thermally access that state under certain conditions, and you can see that on NMR. And so from this DD excited state, it's possible to homolyze the nickel 2 aryl bond, and that would give you a nickel 1 species that can now, it would give you a nickel 1 species and it would give you an aryl radical. And that nickel 1 species can enter what we call a dark cycle, a nickel 1, nickel 3 dark cycle. So a catalytic cycle that can keep the reaction going, but that doesn't need light anymore. And actually, that is the focus of this third paper that I have here, where they really looked at what happens with this dark cycle and how can this dark cycle keep the reaction going. And I want to highlight two more papers that go even beyond the more, they are not just like an organic chemistry group working with an inorganic chemistry group or photophysics group. First, we have this paper from John's works group. John is mostly an inorganic and photophysicist, and they looked at every possible step that these iridium photocatalysts could get involved in this photoredox reaction, this alpha amination that you can see here. So by looking at every possible step, they were able to paint a very detailed description, mechanistic description of this reaction that no one else had done before. Not only is this a lot of work, but it's a really clear picture of what is going on and what are the possible pathways that actually make the reaction worse. And on a different, from a different angle, Beth Alacqua's group has looked at these cycloadditions that happen in polymer nanoparticles. So there is very high confinement of the substrates and of the photocatalysts within these structures. So again, if you are going to forget everything else that I've said, this is a slide to remember. There really is still a lot of room to explore. Up to this point, it has been mostly organic chemists studying photoredox catalysis, but I honestly believe that there is room for a lot of outsiders, if you will, a lot of non-organic chemists. So here are some of the questions and some of the areas within photoredox catalysis that I think there's still work to do. This first part, if we look at the reactants, can we use feedstock chemicals? Like, can we use kind of like waste products? Are there better leaving groups that we could be using? I mentioned before that for cross-coupling reactions, which are similar but are thermal instead of being photoactivated, we need very high energy reactants like Grignard reagents, that kind of thing. Are there other living groups that we should be looking at that are cheaper or safer, lower energy, etc.? Can we move towards green chemistry? And so this first part, yes, it's a lot about organic chemists looking at what can we do in photoredox catalysis. But for example, what about other wavelengths of light? So all the work that I showed you here used blue light. And I would say that blue light is the most used in photoredox catalysis. There is some violet light used and some very low energy UV light that is used as well. But what if we wanted to use lower energy light? What if we wanted to do like green or red? And recently there have been some reports using red light, for example, which is very useful for biological applications because our tissues don't absorb red light. So you can imagine like having photoredox catalysis happening in your body and getting activated just by shining red light on like your hand or your arm or whatever. What if we wanted to, instead of using these very intense lamps as our light sources, what if we wanted to use sunlight? Can we do that? And so I would argue that part of that is photophysics, part of that is engineering, like how do we design these systems? Also, I talked about ruthenium and iridium as fantastic photocatalysts for Redox catalysis. Ruthenium and iridium are amongst the rarest and most expensive metals on Earth. So if we are trying to use Redox catalysis to save the world, ruthenium and iridium are not going to cut it. So how do we move away from that? And a lot of people are looking into this. But it's not just like, oh, I'm just going to take this ruthenium out and put an iron instead, and now everything works. So there's a lot of basic science, basic photophysics, and basic inorganic chemistry, or not basic, but fundamental science to do there to really understand what's going on and how can we use it. And if going back to that paper on the nickel complexes, like that is fundamental science being done there. Also thinking about the products, like I mentioned at the very beginning, that with the very first papers, they were doing an anti-enriched product. So how do we go about controlling stereochemistry, which is not my area of expertise, I will say that, but there is, of course, a lot of interest in synthesizing just one enantiomer or one diastereomer or one conformer or whatever. And so how do we do that? I'm not suggesting that people haven't done it. What I'm saying is that there is still room to explore, and this goes back to Beth Elagwa's group working on these confined systems. What if we can lock where like, the positions of or the orientations of our reactants can we now get a certain stereochemistry? And also, how do we move beyond pharma? I didn't talk about it much, but I said it at the beginning. Pharmaceutical companies have used and have explored Photoredox catalysis a lot. But if you think about this, if we could use feedstock chemicals and we could use sunlight or just like low energy light, how can we use these for other things that are not pharma? Okay? And again, this goes back to organic chemistry. But also, how do we do these at large scale, for example? And so that's more of an engineering problem. So really, I want you to remember that the only way to keep moving this field forward past just organic chemistry problems is to collaborate, and is for us outsiders to get in the field and study the things that maybe the organic chemists focus less on, which is not a job at organic chemists, I should say that. Okay, so as I said, there's a lot of room to explore. Outsiders should definitely get into Photoredox catalysis. And this is the end of my science talk. And now I'm going to use a couple of minutes to talk about Jawscan, which Ben mentioned at the beginning. So Jawscan stands for Just Another Chemistry Webinar Series. And this is a weekly seminar series that we organize. We are chemists, so it is mostly for chemistry and chemistry adjacent research, and it's focused on early career researchers. So either professors or people in industry and national labs who are just starting their careers, but most importantly for students, grads and undergrads and postdocs. Our goal is to serve as a platform, a global platform for anyone to present their science, particularly people who have fewer chances to give talks. This started with when the pandemic hit and there were so many canceled conferences. And we really want to reflect the diversity of chemistry as a field. So we don't just want all white men presenting. We want as much diversity from identity, nationality, origin, ability, background, etc., as we can get. And I keep saying we because I, of course, cannot organize Jawscan on my own. I don't know how Ben organizes this on his own. I have the pleasure to work with these three wonderful people, Madison, Craig, and Monica. And we also have a bunch of volunteers who also help us a lot. And currently we have support from Cell Reports Physical Science, Merck, and the Royal Society of Chemistry. So Ben mentioned this at the beginning, but if you want to follow us on Twitter or on Instagram, it's at Jawscan. And you can also learn more about our seminar series or submit your abstract, wink, wink. You can do that at jawscan.com. We recently finally got our own website domain, and we're pretty excited about that. So please check us out. We are gearing up to start back on September 21st. You heard it here first. So September 21st, Jawscan comes back. So please submit your abstract so that we can showcase your amazing science. With that, I will thank a couple of people. There's actually a ton of people that I should thank. Those are the three groups that I was part of during my career. So the Baraldo group, the McCusker group, and the Macmillan group. I also want to thank my wonderful colleagues at K College. You can see them right there. And here on the right, you can see my research lab, my wonderful students that work with me this summer. But actually, my favorite picture is that one. The person covered in toilet paper is me. That's how respectable I am as a professor. Anyways, with that, thank you everyone for listening. Thank you again for the invitation, and I'm happy to take any questions.
That's a fantastic picture. All right, so we will jump straight into it. So we've got a few questions here from along the way. So this one was from near the beginning of the talk. Does the amino acid need to be cyclized, or can it be linear?
I believe it can be linear.
Okay.
Yeah, of course, there's a big scope table in the paper. Mm-hmm. Since I'm not an organic chemist, I kind of gloss over the scope tables. Sure. And I look at the mechanisms more. But no, I believe that there were some examples that were linear.
Okay. Let's see. So, what makes the bigger difference for the Photoredox catalysis? Is it the transition metal itself, or the ligands attached to it?
Ooh, that's such a great question. Bit of both. It really depends. So it all depends on a variety of things, right? So it depends on what redox potentials are you shooting for. Mm-hmm. And so, for example, if you have those phenylpyridines, those are actually negatively charged or formally negatively charged. Mm-hmm. So your metal center is much more electron rich from the get-go, which means that it is actually much easier to take electrons from it. Mm-hmm. So depending on what metal you have or what ligands you have, you can really tweak those things. You can also change the energy of your excited state. So for example, the iridium photocatalysts tend to have higher excited state energies compared to the ruthenium ones. And so, yeah, it really depends on what you're going for. Mm-hmm. Stability can also be a thing.
Sure. Oh yeah. Yeah. Stability is always a big issue.
Yeah. So there's a bit of everything. I think one of the biggest things is that in general, iridium complexes tend to be yellow, so they actually emit their excited state energies are higher, which also buys you more oomph towards redox potentials as well.
That makes a lot of sense, and yeah, you're right. They do tend to be pretty high energy. So this was a question that I had, and might delve into it a little bit more. Could you envision mounting or depositing these photocatalysts and transition metal catalysts onto some kind of supporting or some kind of conductive support and accomplish the same type of result?
Oh, that's my dream. So let me tell you my dream, and I'm hoping that some engineer, wink wink, listens to this and brings my dream to fruition.
Okay.
I don't even need to work on this. I just want to see it published. My dream is to have essentially like a stick, like a photocatalyst stick, right? Like imagine like one of those like microscope slides.
Yeah.
Imagine that. And you put your photocatalyst and maybe your nickel catalyst there, and so like you dip it into a beaker with your reactants. You dip it in there. You shine light, reaction happens, you take your microscope slide, you dip it in your next batch, and you keep doing that and you recycle it. That is my dream.
I think you could do it, honestly.
I mean, I think that someone has to be able to do that. And I feel that it would be really cool from a variety of things, right? But I also think that, again, you need some organic chemists who want to test it, but you need some engineers who want to design it. And so we toyed with it a little bit when I was a postdoc, because I brought up this idea to someone, and part of the problem was finding the right photocatalyst / catalyst pair, but it was also a matter of things desorbing, and we had some gels that were dissolving and leaching and stuff like that. So it's not a trivial problem, but I think it's 100% doable. So I'm gonna use this video to claim some credit when someone publishes.
Perfect. It. There you go. I think, at the very least, you need to be in the acknowledgments, no doubt. I think it could be done. The reason I asked that was when I was in grad school, we had somebody that worked with graphene oxide. They used some quantum dot or something like that. I forget what it was. It was a photocatalyst of some kind. So it was like a, not molecular, but something like that. Right. And they could store charges on the graphene oxide and then use those charges to, in this case, they used like silver reduction from silver plus to silver metal, just to demonstrate that they could build these charges up and do it. And that's what makes me think that something like that ought to be possible. Like you said, there's a lot of tricky parts, like having it leach off and that kind of thing, but it definitely seems like it should be doable.
Oh yeah, no, I think so, and so part of this, so it's similar to like what a dye sensitized solar cell is, but so and again, it would be a matter of, because we were also thinking like, can you, like, how would you design it? Would you like sandwich it? Would you like have everything just spread out? Because how do you get it so that, okay, this absorbs the photon and then this does the catalysis. So like you have to have like, how do you illuminate it? It's not trivial, but it's totally doable. I'm convinced that it's totally doable.
Yeah. Along the same lines, what's the efficiency of that energy transfer that has to happen between the photocatalyst and the transition metal catalyst?
It's pretty high. I don't have a number off the top of my head. I don't think we looked at the efficiency, because so part of the problem is that in many of these cases you have competing, so you can have both electron or energy transfer happening.
Sure. Okay.
In the particular case of this reaction, the iridium PPY3 wouldn't oxidize it, so you had almost exclusively energy transfer. But I'm trying to come up with a number. I'm not going to give you a number, because I'm going to just like BS my way through it. But it's fairly high.
It's fairly high.
The quantum yields of these reactions are not that high. Actually, John's work did a great job of with his group. They did a great job of like measuring the quantum yield of this reaction. If I remember correctly, it was about 30%, I believe.
Okay.
For the reaction that they were looking at. So like, how much product do you get per photon that is hitting your solution?
Yeah.
But even with that, so essentially that's how that's part of how you can explain the longer reaction times. Like if your quantum yields were higher, your reactions would probably take less time. But there's a lot of photon losses in different places.
Oh yeah, absolutely. Okay. Iridium. So the question here is: are iridium and ruthenium more expensive? Has anybody tried anything with iron and cobalt complexes?
Yes. So I would say that this might be a bit of a controversial statement,
Good.
but no, I would say that this is something that inorganic chemists and photophysicists are very interested in.
Mm-hmm.
So there is a lot of work that is being done on moving away from ruthenium, for example. So ruthenium is the star of the show, or was the star of the show when it came to dye-sensitized solar cells.
Oh yeah.
And so a lot of people, the McCasker group where I hail from included, it was not my PhD work, but a lot of people there too are looking at what if we use iron complexes instead of ruthenium complexes.
Mm-hmm.
As far as I know, there is less on cobalt. There's much more on iron, but there is a lot of work on that. So a lot of inorganic groups looking at the photophysics of iron complexes. There's copper polypyridines have also been used. There's some beautiful work on zirconium. So in those cases, instead of MLCTs or LMCTs, yeah. Of course, now I'm blanking on his name. Carsten Misman. Sorry, Carsten. Carsten Misman has done some beautiful work on zirconium complexes with LMCT excited states. He has there's one paper that's a collaboration also with Phil Castellano looking at that. So like lots of beautiful work along many areas. Oliver Wenger has done some work on both chromium and molybdenum as earth abundant alternatives as well. So there is a lot, I would say, from the inorganic / photophysics side. There's much less than on the organic side. And this is why I keep saying like, hey, let's be friends and collaborate. Because the classic example that you find is well-meaning inorganic chemist designs this compound and is super excited about their compound that is so cool, right? And then they try to test it in a photoredox reaction, and they test it in what organic chemists will tell you that it's a very boring photoredox reaction. And so they are much less excited about it because, organic chemists is like, well, yeah, but you can do that with ruthenium, or you can do that with iridium, so who cares?
Yeah.
Right? Or yeah, but no one uses that reaction because it's, I don't know, not exciting for some reason, right? And then inorganic chemist is sad because their shiny, beautiful compound is less exciting, right? And so I think that's one of those points where you really need the dialogue, right? Like, hey, I am organic chemist and I need a compound that can do this, or I'm interested in this reaction. Hey, you inorganic chemistry friend, can we find a compound that is cheap, and that also can do this?
Yeah.
This is part of why I was so excited when I saw the Doyle-Scholes Castellano paper on those nickel complexes, because I thought it was really nice how they looked at the photophysics of nickel complexes. And it started as let's understand how these photoredox reactions work. But then it went on to, hey, like, it was a beautiful basic science paper.
Yeah.
Right? And I thought that was really cool. So going back, because I went on like 3 different tangents. So going back to it, there is interest in doing iron and cobalt. There is some work along those lines, but it's, for the most part, there's some iron work that is organic, like organic photoredox iron work with very little insight into the mechanism. And then there's a ton of work on how cool iridium polypyridines, iron polypyridines are, but with very little application to photoredox.
Okay. This is something just for me because I'm still learning a lot about this area. How do how do the oxidation states of the metal center matter a whole lot beyond, I guess it seems like it's mostly determined by the energy level, like where the redox potentials of the complexes end up being. Is that more what determines it, or is it like stability of the metal center, oxidation states, and things like that? Because like I know iridium, for instance, can go up to 6+, but it doesn't really like to, it doesn't stay there very well, right? So
Right. Yeah. So I feel that the answer is yes, but you asked several questions.
Yeah, sorry, I started to get going.
No, you're totally fine. I'm laughing at myself because I end up with the classic yeah. So I would say that in a lot of cases the exact oxidation state is less important, right? If you need an oxidant and you have a transition metal that can access two different oxidation states, like N and N+1, and your redox potentials are right, it doesn't matter. So case in point, root tris-BP is a ruthenium-2 compound, and iridium, all these iridium complexes are iridium-3 complexes. And in many cases, one or the other can catalyze the reaction.
Okay.
Right? And so it doesn't matter as much. Like, yeah, ruthenium can go to ruthenium-3. Okay, so now it's oxidized. Iridium can go to iridium-4. Now it's oxidized. But it doesn't really matter what the numbers are or like what the oxidation state is. What matters much more is the redox potentials and the excited state energies.
Okay.
And so yes, that's not completely independent of the oxidation states.
Sure.
Right? But it's not like you wouldn't say, okay, I need a metal 3+ photocatalyst. You would say, I need a photocatalyst with this reduction potential or this oxidation potential.
Okay, that makes a lot of sense. Let's see. Next question here is, do you know if anyone has made a supramolecular analog with a covalent linker between the photosensitizer and the nickel catalyst?
Yes, there's one paper that came out in, I want to say like 2017, something like that, where they made a MOF that incorporated both iridium and nickel. And I don't remember what reaction they did, but it was not that exciting, apparently. So again, it was again the same idea of well-meaning, excited MOF chemists made this super cool MOF that had both an iridium photocatalyst and a nickel catalyst.
Yeah.
But then the reaction that they tested it in was not earth-shattering.
Okay.
And so I feel that, I don't know, and granted, it's not like I keep up on who cites what.
Right.
But I felt that paper wasn't as appreciated as like it could have been because it was really cool.
Yeah. I mean, that sounds really cool.
Yeah.
You get it built into one.
No, yeah, it's really cool. And like going back to what Beth Elacqua's group is doing, like this idea of, which is something that people who work with MOFs do a lot, right? Like what happens when you have these four as like a nano vessel, right? And you put two molecules, and these two molecules are in fixed orientations because they don't fit anywhere else.
Yeah.
Like what can you do now? And one problem that I did not talk about is that one of the biggest problems, particularly like going back to this iron complexes thing, is the lifetime of your excited state, right? So these excited states that can do oxidations and reductions and energy transfers and whatnot, they have to live in solution for about a microsecond, well, hundreds of nanoseconds. They don't need to be a microsecond long, but they need to live for like hundreds of nanoseconds so that they can diffuse from point A to point B in the solution and get to the substrate that they're going to react with. One of the big problems with iron complexes is that iron complexes, usually it takes a couple of picoseconds for them to go from an MLCT to a ligand field state, and ligand field states have a different reactivity. So those lifetimes are super important.
Yeah.
So going back to the idea of like supramolecular things or like fixing things, like if you can put your photocatalyst and your nickel catalyst, or your photocatalyst and your substrate right next to each other, now these things don't need to diffuse towards one another.
Right.
So again, you could potentially do more things. Right.
Okay.
The other problem that I will say is, so it's also a matter of design. So one of the things that if you talk to like a hardcore Photoredox catalysis person, they will tell you that one of the cool things is the modularity.
Yeah.
That you can like kind of plug and play and like take different iridium photocatalysts depending on what reaction you're trying to do, and different nickel catalysts, or there are other as well. Whereas if now you have to design this MOF, synthesize it, characterize it, and like you can only use this MOF, now you have limited some of your applications, right? Since I'm more of a basic science kind of person, in case you couldn't tell, I think that those MOFs would be beyond cool.
Oh yeah.
Right. But there's the caveat that if you're going for like widespread applications, you might be limiting yourself, whereas like modularity is much cooler in that case. Right. But I think that there's, even within those parameters, there's still a lot to do there.
Sure. Oh yeah, absolutely. Well, and it may be the case where, you can sort of set out like a baseline MOF, like, okay, here's how you can do it. And then you start playing around with, can you change some of the substituents and things like that and still get that basic MOF. Okay. So it looks like we got one more question here, and this one I feel like is the most important one. Was Bandit the guilty meower?
No, it was Berta.
Busted. All right.
Yes, Berta. I was actually going to say something when she was meowing. Yes, yep. Berta was she's now laying on the floor right next to me, being like, "But when is my time?"
Yeah, exactly. So. I mean, fair.
I know. Yeah. No, that is true. It makes me very happy to know that people know my cat's names.
They're very popular.
I feel that I've made it.
That's good. Oh, goodness. So I think that's all the questions we have. If anybody has one that they want to get in at the last second here, please feel free to do so. But I will go ahead and start wrapping up a little bit. Thank you again, Dani, for coming on. It's a great talk.
Thank you.
It was really cool to see the work that you've done, as well as get an appreciation for the field of what people are working on and where it's kind of going. Like I said,
Thank you.
I did a little bit of photochemistry, but this was outside of my area of experience, so it was really cool to learn about it. And I'd like to thank everybody for coming out. Great to have everybody here. I hope you'll come out again next week, and for weeks following that. Next week we have Dr. Paulette Vincent Ruse.
Amazing talk. You should totally go.
Excellent. So we'll be back here again next week, and I think that's everything, actually. So thank you, everybody, for coming out. I'll drop the Discord link one more time. Certainly feel free to join that if you would like to. It is also, like I said, very, very low-key and relaxing, and we'd be happy to have you. And Dani, if I can get you to hang around for just 1 second, we'll chat very briefly. And for everybody else, have a good weekend. Stay safe. I'm going to bet everybody here is vaccinated if they can be. But if for some reason you're not, get vaccinated.
And wear your mask.
Yes, thank you. And also wear your mask. It's been 18 months. We know what to do. Let's do it. Kind of tired of this already. And otherwise, have a great weekend. Enjoy Labor Day. So enjoy your long weekend. And we'll hopefully see you out here next week. And thanks again for everybody for coming out. Have a good night.